Lesson 9 is on Coulomb's law. And before we talk about Coulomb's law, we're going to just very quickly review another law, and that's Newton's gravitational law, which you should remember from Physics 20 as being Fg, the force of gravity between two masses, is the universal gravitational constant times the product of the masses divided by the distance between them squared. So what does that measure? It measures the gravitational force between two objects with any given mass at a given distance. And just to review, this is essentially what Newton came up with. And Newton came up with this. He realized that the gravitational force was proportional to the product of the masses. So if you increase the masses, or you increase one mass, and the gravitational force will increase, and was inversely proportional to the square of the distance. So if you double the distance, 2 squared is 4, so the gravitational force will be 4 times less. In other words, it will be a quarter of what it originally was. So that's what Newton came up with. And then it took, he wasn't able to figure out this value here, G. Along came Henry Cavendish, and he calculated the value of G, which equals, on your formula sheet, 6.67 times 10 to the negative 11. And then if you want the units, newtons meters squared per kilogram squared. Okay, and that's just so all the other so that this cancels and this cancels and that cancels, leaving you with newtons. That's why the units for the gravitational universal constant are such. Okay, so that was that's the gravitational force between two objects. Newton came up with the idea, Henry Cavendish came up with G, and then we end up with this this formula right here that measures the gravitational force between two objects. So now we move up into the 18th century, and we have this guy, Charles Augustin de Coulomb, and he wanted to measure the electrostatic force between two objects. So in the, we've already determined that if I have an electron and, an electron there and a proton here, that they are electrostatically drawn towards each other. De Coulomb wanted some way to measure that. And not surprisingly, as a testament to the symmetry of the universe, Coulomb's law turns out to be remarkably similar to Newton's law of gravitation. In other words, it's an inverse square law. And okay, we read over our notes here. It says, this is the important stuff right here. Right here, it says that one of them, published in 1785, discussed the inverse square law of forces between two charged particles. The inverse square law. The electrostatic force is inversely proportional to the square of the distance, or the distance squared, I should say. This just means that if you move the charges apart, the force between them starts to decrease faster and faster exponentially. In a later memoir, he showed that the force is also proportional to the product of the charges. He showed that it's proportional to the product. Oh, Q, haven't seen that before. Q is the letter we're going to use for charge from now on. And yeah, you can see how that is incredibly similar to what Newton came up with for his work. In a later memoir, he showed the force, yes, the product of the charge is a relationship now called Coulomb's law. For his work, the unit of electrical charge is named after him. Okay, so this is great. Just as the unit for force is a Newton, the unit for gravitational force, the unit for electrostatic force is named after Charles Augustin de Coulomb. So it's a Coulomb. A Coulomb, an electrical charge, is measured in coulombs. So you know you're good when they name something after you of that importance. The charge, we measure the charge of objects in coulombs. How did he do this? Well, he used this system or an apparatus very similar to what Cavendish used. Cavendish He used a torsion balance. And we'll watch a video on torsion balances, or you should go to YouTube and watch a video on torsion balances just to remind yourself of how they work. They're quite the one they used was quite ingenious because essentially what he had a ball and then he charged this ball here and he saw that they were electrostatically repelled and then he took this one out and touched it to another one that was the same size. So when he touches, he takes this purple one out and he touches it to this blue one, and then he knows that because they're the same size that they will share the charge equally. So now this purple one has half the amount of charge that it did before he touched them because of the conservation of charge. Remember, we touch two objects together, they'll share the charge equally. And then he went and repeated this and measured how much this thing, so then this thing would have not have been repelled as much, so it would have been closer, measured the angle, did all kinds of mathematical calculations, and that's how he came up with the fact that the electrostatic force is an inverse square relationship. So quite ingenious. Remember, we're talking about the 1700s, 1750 or 1760, around there. Pretty cool. That was the same time that Mozart was living. Very cool. Okay, so you can read all that. I kind of just described what he was doing there, and that's what he came up with right here. This is the formula for the electrostatic force between two objects. And again, just to drive this point home, it is remarkably similar to the gravitational force between two objects. What's different? Obviously, the constant is different. So remember, Newton had to come up with a number that would make this relationship here work for everything in the universe. And he couldn't do it, but Cavendish did come up with that number, the universal gravitational constant. Coulomb, same thing. He had to come up with this number here that would make this relationship work. The product of the charges divided by the distance between them squared, and you have to come up with a number so that would work for universally for any two charges you could get. And he came up with that number. It turns out to be my formula sheet. I want to make sure I get this right. As written on your formula sheet, K turns out to be, where are you? 8.99 times 10 to the exponent positive 9. And the units, you could probably deduce what the units are. Remember here, we have kilograms, and then we have meters squared over here. So we have kilograms, meters squared. So the units for G turned out to have the meters squared on the top and the kilograms squared on the bottom, so they cancel each other out. Well, this is the same kind of principle. Charge is measured in coulombs. So that's a coulomb times a coulomb, which is a coulomb squared, and distance is measured in meters, meters squared. So the units for the K value are newtons times meters squared per coulomb squared. Why is that? It's so that this meters squared will cancel out this meters squared. This coulomb squared will cancel out this coulomb squared, and we're left with newtons. Newtons. Right? So that's why they have these crazy units. Oh, it's right there in your notes. All right, and then it says we calculate the absolute value just to get the magnitude of the force. So let's do example number 1 here. This is definitely going to be a 2-part lesson. Example number 1 says a comb with 2. Whoa, what's that crazy symbol? That is a microcoulomb. Micro. Look on your formula sheet and it will tell you what that is. A micro is times 10 to the negative 6. So just so you know, we're going to be dealing with some very small numbers when it comes to charge. If somebody said, I'm going to give you 1 coulomb of charge, you should say, no thank you, and get the heck out of there, because 1 coulomb of charge is essentially the charge of a lightning bolt, which is going to be unpleasant to receive. Here we go. We've got the, so I think we're good on this. We've got the charge of one, so that would be Q1. We've got the charge of the other, so that would be Q2. We've got the distance between them, so that will be R. We have a formula, and we just plug the numbers in. Pretty straightforward question. 8.99 times 10 to the exponent 9 times 2 times 10 to the exponent negative 6 times, now this one is positive and this one is negative. So in other words, this has an excess of electrons, and this one has a deficiency of electrons, deficiency. Do we put the negative into the question? No, you can if you want, but all of this means is that they have opposite charges, therefore they are going to move towards each other. Okay, so putting the negative into the question it can be misleading, so I wouldn't do it if I was you. Leave the negatives out and then just use the negatives and the positives to determine what direction the hair or the comb, whatever they're talking about, goes in. And then the distance between them, it's got to be in meters. It's 1.5 meters squared. Get the answer. The answer is 2.4 times 10 to the negative 2 newtons. Now, actually, sorry, I should have been a little more specific about this. We should have drawn at least some kind of diagram. We've got a comb, and it's to the left of the hair. So here's the hair, here's the comb. And we are asking, they're oppositely charged, so they're going to be drawn towards one another. Determine the force the hair exerts on the comb, which is kind of odd because obviously probably because of the mass of the comb and the mass of the hair is going to be going towards the left, but the question says determine the force the hair exerts on the comb. So the hair is going to pull the comb because they're attracted to one another in that direction. So the answer to the question is 2.4 times 10 to the negative 2 newtons to the right. Right, and if it asked determine the force the comb exerts on the hair, then it would be 2.4 times 10 to the negative 2 newtons to the left, because the comb would be pulling the hair to the left, again, because they're attracted to one another because they have opposite charges. So that's how the positives and the negatives come into play. Again, they're not really, if you put them into the question, you might confuse yourself as to direction and so on. Okay, so that's part 1 of lesson 9. On to part 2.